So the first thing is areas between curves. Okay, so first we look at the meaning meaning of areas between curves in terms of Riemann sums. Let us draw a typical picture. Okay, so this is x-axis, this is y-axis. So one curve is like this. Suppose the other curve is like this, and we want to find the area between them from this point to this point, B. So this is y equals f of x. This is y equals g of x. So we are interested in the area in between. So what we do as far as the Riemann sums is concerned is we subdivide this into small pieces like this. Okay, so for example, we can take this one. So here we look at, here we choose an arbitrary point. Let's say, okay, so let me put an arrow xi star. So remember that we are doing this with sampling points. And then we look at this height, and we consider this. So this point also goes here. So it is this height now. Okay, so we calculate this height. So this distance is delta xi. Okay, and we want to look at the height. Height is, in this part, this height is the length of g of xi. Okay, so this is, but in this picture, g of xi goes downward. So this height, this is g of xi star. I'm only interested in the length, but in this case, this is minus gxi star, since here in this picture, g of xi star is less than 0. It's negative here for this part. Okay, and this distance here, so this is again, we are interested in this height, f of xi star, but here this is positive, so I have xi star. Okay, so total height. So if you look at this one, total height, this height is f of xi, f of xi star minus g of xi star. Okay, so I have this height and this base. Okay, so this triangle, this rectangle has area f of xi star minus g of xi star times delta xi star. Well, star, not star, that one is xi. And the Riemann sum approximating the area between the curves is you sum up these things. Okay, you have f of xi star minus g of xi star delta xi. Let's draw a similar picture where gi is not negative. So another picture. So in this case, we want to look at it like this. Okay, so this is y equals f of x. This is y equals g of x. So again, let us do a box like this. Okay, so we have this thing, and here we have xi star. So we look at this height. So that gives us a box like this, and it gives us this height, and it gives us a box like this. So in this case, we are interested in the area of this box. Okay. So the total height this time is clearly the difference between them. Okay, so this height here is f of xi star minus g of xi star. And this is again delta xi. Okay, hence the Riemann sum becomes the same thing. So hence the Riemann sum is the same as before. So the Riemann sum, you add up the heights, g of xi star delta xi. Okay. So if f and g are continuous, the limit of this Riemann sum exists and is denoted by integral from a to b in both pictures. Okay, so here again, let's put, we started from here, a to b, f of x minus g of x dx. Okay. So this is theoretically how you develop this theory, but when nobody is looking, you can have an interpretation of this. An interpretation of this area integral. Okay, so let's look at a picture like this. So let us assume that one g of x is 0. So suppose we have f of x from, say, a to b. I want to understand this picture, x, y. Okay, so we know that this shaded area is given by the integral from a to b f of x dx. Okay, so this is how you interpret this thing. Given any point x here, okay, any point x here, you look at this thick line, okay. The length of this is f of x, and then you see that this length is here. Okay, the length is given at an arbitrary point. The length is given like this. Then you look at the thickness of this. Thickness of this line, okay, so this is just an interpretation, is dx. So that's an interpretation, okay? And that thickness is now here. Okay, so here you see that you have a small area. Okay, so consider this physically. Suppose I have this line here, not mathematical line, but when you draw it with a marker like this, you have a line which has a length and a width. Okay, so it has a thickness. So I move this around and paint all of this. How much paint did I use? Okay, so I first of all calculate the height of this and the thickness of this, and then I add these things up at every point. At every point, I have a different height, the same thickness. Okay, I'm interpreting this. So I get an area. So we call this incremental area. Okay, so sometimes this is denoted as dV. Well, dA. We'll come to dV next hour, dA. Incremental, this is, you can interpret this as incremental area. Okay? So what you are doing is you calculate the area at a small place and you add up all possible areas in here. So you paint this, you paint the whole thing and you get the area. Now this interpretation is important. It is trivial in most cases, but you have to keep in mind that this dx is interpreted as the thickness of the value you have here. Okay, so now you have an area. You are multiplying two things and you are getting area. In volumes, we'll also look at the same thing from this point of view. So it's easier to interpret this thing. And once you understand what's going on here in terms of this interpretation, you are going to add these values multiplied by their thickness, and you add them up. You get the total area in this case. Okay, so let's do this on examples. In examples, what's important is, of course, most of the time, the trick will be to set up the integral. Once you set up the integral, then the rest is easy. If either the function is easy, you find an antiderivative, or you use a software, or you use numerical methods. But so your responsibility is to set up this integral correctly. Okay, so let us look at these examples now. And in order to set up these examples, the important thing is, of course, to find limits of integration, which function is larger than the other, etc. So let me look at this one now. One, find the area enclosed by the parabola y equals x squared and the line y equals 3 minus 2x. So in these problems, generally there are two curves. And when you have two curves, there are lots of regions. And most of these regions are unbounded. And of course, we are not asking the area of an unbounded region. The answer is unbounded. So to indicate that we are interested in what is reasonable, we use the words like enclosed or the area between the curves, bounded by these curves, etc. So you draw these two curves. In this case, it is simple, but in general, this is what you do. You have two curves. Okay, you plot these two curves, and then you find the region bounded by them. If the problem is just like this, you find the bounded regions between these two curves, and you calculate the area. You set up the integral. Sometimes the problem continues saying that find the area between these two curves between this point and that point. Okay? Then you again plot this. We'll do examples like this. And then you just look at the straight lines, x equals this and x equals that. So now you have four lines, four curves, two perpendicular lines, this curve, and they enclose an area here, and you set up the integral. Okay, so let us start with this thing. So the picture here apparently is something like this. So you have this parabola, and you have this line, x, y. Okay, so this is here. Okay, so in this problem we also have this following thing. So if we leave the problem here, okay, so let me do it this way. So if the problem is this much, we understand that we are going to calculate this area. Okay, so to make this problem interesting, it says between x equals minus 2 and x equals 2. So in my okay. So first we draw these, y equals x squared and y equals 3 minus 2x. So the first thing is to find these important points. Okay, so you see that these points are important in our understanding this thing. Okay, so what are those points? Which one? I have 4 points. Let's start from this one. Minus? Minus 3. Well, I don't have minus 3 here. How come you have my... Maybe I have minus 3 here. Let me check. Okay, let's see. You intersect these things.
Minus 3 minus.
X squared equals 3 minus 2x. So x squared plus 2x minus 3. And you solve for x, 2 of these. So this is minus 1 plus or minus square root 1 plus 3. Oh, this is a cooked up example. Okay, so minus 1 plus or minus 2. And what did you say? Minus 3 and 1. Okay, so this is minus 3 and 9. And this one is when x equals 0, y equals,
Why do we need to?
when x equals 0, y is 3. Huh?
Why do we need to?
Well, you have to understand what's going on. So first of all, we want to have complete command of what's going on. Because you see, we will put x equals minus 2. Shall I put x equals minus 2 here or here? Okay, you have to understand totally what's going on. So what is this point? This is 0, 3, 0, 3. Okay, so what is this point? We found that x equals 1, y is 1, 1, 1. And this point is when this is 3 over 2, right? 3 over 2, 0. Apparently now we have to change the picture. You see, this thing goes a little bit. If this is 1.5, 2 is somewhere here. Okay, so this thing goes up like this. So 2 is here. And okay, so this is 2, and I have minus 2 here. Okay, so the area, apparently the area, let's draw it red so that it gets our attention. Okay, so this is the area that we are interested in. Okay? Everybody agree with this? So you see, this is recorded. If there is an error, it's your responsibility. Okay? I check if the class is awake or not. Okay, so you agree with this. Then we continue with setting up the integral. Okay, so the only reason this is given as an exercise is that if you blindly write this minus this and take the integral, you will not get anything relevant to this one. Okay, so here this line is above, and here this curve is above. So you have to you have to pay attention to this. So this is the point 1. Okay, so area between the curves is given by the integral. So from minus 2 to plus 1, I have a certain setup. This line is on top. You see, I'm interested in the thickness. So let me emphasize this interpretation. This is not... How about this? Okay, so I'm interested in this line, the length of this line, and here the thickness. Okay, and so the length of that line is this number minus this number. So let me. So this point is x squared, right? I'm on the parabola, and this point here is x, and y is 3 minus 2x. So the length of this thing is this minus this. Okay, so and this holds from minus 2 to 1, minus 2 to 1, and the height is 3 minus 2x minus x squared dx. Okay, height of the line times the thickness of the line. So this gives me an area, and I add up all these areas. Okay? But when you want to say this technically, scientifically, you say I integrate all these values with respect to x. Okay? So that's the scientific way of explaining this, so that nobody understands that you are actually adding up small boxes. Okay? So this gives me the area from here to here. Now, I look at the situation here. Here the situation is reversed. I want the length of this line at a point x. Okay? So now it is all upside down. So this point is now, if this is x squared, and this point is x, 3 minus 2x. Okay? So plus that area. That area is now from 1 to 2. And now this is x squared minus 3 minus 2x. This is the length of that line times the thickness of the line, dx. Okay, so the area is given by this thing. Okay, so you see from here on, it is just routine. Okay, so this here you have a polynomial, here you have another polynomial. You just integrate these things and you get 11.1 over 3. So that's what I found. Okay, so the integration is easy in this case. The important thing is to set up the problem. Okay, so here the picture is easy. The functions are easy. Why did we do this very slowly? Because this is the process, no matter how complicated the situation is. You have to have a full understanding of the graphs of these things. You have to understand from which point to which point you want to calculate the area. So this is the picture. Once you have the picture correctly, then you try to find heights and multiply them by the thickness dx and add them up. Okay? When the curves cross each other, the expression for the height may change. That's the only thing to pay attention. Okay? So let's look at another problem. Okay, so the next okay, so find the area bounded by y equals x over 2 cube root and y equals x minus 1. Okay, so again, the procedure is the same. Just because we have complicated looking functions doesn't mean that we change our approach. First, you sketch a graph. Okay, so this one. So this one is a cube root, so it will probably be something like this. And here in the problem, do I take, no, okay, so the problem is this. So it will be something like this. Okay, oh, no, not this one. This is cube root, so it goes to the other way. Okay, so this is y equals x over 2 cube root. And then you have this y equals x minus 1. When x is equal to 0, y is minus 1. So we have this. Okay, so let's do it this way. Okay, so this point, what is this point? So this one is y equals x minus 1 to what? 2, x equals 2, y equals 1. Okay, so is this the only solution? Does this thing, maybe this thing comes and, huh?
Is this one is true? But I don't know that.
Well, you have to check. Well, I'm waiting for you to check. Did I draw this correctly, or maybe it is something like this? Okay, so it is like this, and this is like this. So this is 1 here. What is this point? When x is 0, y is minus 1. So this is minus 1. Okay, what are the coordinates of this point? Well, next week you have a midterm. Let me just stir you up a little bit. So in the midterm, which figure do you draw? This figure or this figure? I'm waiting for you. So you expect that I'll wait for a few seconds, then I'll go and solve it. No, I will not do this. The camera is rolling, the class is thinking. The class is thinking. Huh? Efendim? Did you attempt? Okay, so you are calculating this. You are trying to solve these things. If you have cube root, this means that this thing is y cube is equal to x over 2, or x equals 2y cube. Do you have a solution for this? Any solutions? We are waiting. The camera is rolling. So this will be on internet forever. A class of engineers trying to find if two lines intersect or not. Okay, so what? Do they intersect or not?
Kesişmesi alan sonsuz olmaz mı?
Now, don't come to those points. So we have a simple questions. Is this the correct figure or is this the correct figure? Which one?
Alttaki olmak zorunda mı? Bilmiyorum, hesaplamadım.
Well, this is something that we don't want to hear from an engineer. I didn't calculate it, but the answer is this.
Can we use Wolfram?
Of course.
Okay,
Okay, so we have one vote for the above one. Let's see. Let's wait for the other votes. Nobody cares, huh? Just one person. Yes? Huh?
Can we float sanat kökleri gösterebiliyoruz mu?
No, the sanal kök are imaginary roots and they are not on the real line. So they don't exist for us. So you say there is one root. Okay, if there is one root, we already have one root here. So what happened to Wolfram? Is Wolfram still thinking?
I'm writing
I said above.
Okay, so we have two votes here.
I don't know how to do.
Okay, so let's go for the 3-1. So did you calculate it?
I tried, but I tried to integrate Veluter, but
So let's try this Wolfram stuff. What does Wolfram give to this equation? Okay, so I want to intersect this with this. So from here I have y is equal to x 2y cube minus 1. So what are the roots of this? Y equals 1 is a solution. Okay. Yes, how many solutions do we have for this? So you say there is only one solution, y cubed minus y minus 1 is equal to 0.
We know that one point that is
Yeah, we know one point is y equals 1.
and we can make a polynomial
So, okay, I understand your point. So I divide it like this, y minus 1. Okay, so this point. So what did you find here? 2y. Okay, the first one is 2y. 2y square. 2y square minus 2y square. We subtract this, we get 2y square minus y minus 1. So apparently I need 2 here, right? 2y. And this is 2y square minus 2y minus 1. So how come we didn't divide this? So I subtract these things, I get y minus 2. Okay, and then well, we don't have this, right? Y minus 1. And then we have plus 1.
And that doesn't have real.
And we look at the discriminant. So what is the discriminant? 4 minus 8, right? Negative. No other real roots.
Do you want to see the graph?
Huh?
Do you want to see the graph?
No, we now, with your friend's help, now we totally understand the graph without Wolfram. Okay, so we can send Wolfram home. You see, it wasn't that difficult. Okay, all you needed was confidence that you can attack this problem. So just you see y cube, I can solve y cube, I'll go home. That doesn't work, okay? Just try your best. Okay, now we totally know that these two lines intersect only at one real point, and as your friend showed, there are two imaginary solutions, one conjugate of the other, because the coefficients are real here. But since we are drawing a real graph, this is the picture, okay? So this is the picture. Okay, so let's go back to the problem now. This is 0, we know this. So the area bounded by these things is now, we know, is this thing. Okay? The area between these is integral from 0 to 2. From 0 to 2. So I'll write a typical thickness here. So let me again do it with black. We are used to this. Okay. So this is at a typical point x, this is the height. Okay. So we know that this is this function, x over 2 cube root minus this function. This function is x minus 1 dx equal, okay, so I will calculate this. So this is the area. Okay. We can calculate this, no problem. But in this problem, we can see it. You see that we solve these things, changing everything to x equals something. I can also change this to x equals y plus 1. So I have these two things. You see that the equations for these are easier. Not that this is difficult, but just to add something to our repertoire, we can write the same integral also. Now I live along the y-axis. Okay, so let's find a different color for this. At any point, I'm interested in this thing. Okay, so here, let's see. At any point y, I am interested in this distance. Okay, so that distance is also, so this thickness will change from y equals minus 1 to y equals 1. And the length of this thickness is this function minus this function. So this function is this one, y plus 1, minus the other function is 2y cube. Okay, so this function is x equals 2y cube, and this function is x equals y plus 1. So that's the distance here. Now I multiplied with the thickness. What is the thickness of this thing? I move a little bit in y, dy. Okay, so both integrals should give you the same number. Okay, so I calculated both of them, and believe it or not, both of them give you 1. Okay, so this thing is 1, and this thing is 1. Okay, so what we learn from this exercise is that sometimes it is possible to change your point of view. When you change your point of view, sometimes you get a simpler function. Okay? If you are doing this, of course, with a computer, the difficulty of the integrand doesn't matter, but sometimes even the software gives you quite ugly results. So you change your point of view and you get a better expression. Of course, you'll get the same number when you are interested in the number, but if you are after expressions, sometimes you want to simplify things. Okay? Any questions so far? Okay, so let's see what we have. Okay, so these are all the same thing doing several times. Okay, so let me do one more about this y stuff. Okay, which one is easier to erase? This one. Okay, so the problem here is find the area enclosed by y equals x minus 1. Okay, so our favorite, it turns out that this is our favorite line. And y squared equals 2x plus 6. Okay, so again, the first thing to do is to draw a picture, find the intersection points, etc. So now, since this doesn't say find the area between these two curves from this point to this point, we will draw these things. We have a parabola and a line. So the line will cut some portion of the parabola, and there will be an enclosed region, and we want to find that thing. This parabola is turned to the right or to the left. Okay, so this is not a parabola like this. This is a parabola like this because of this. X equals y squared. Okay, generally thinking. So it is like this. It increases as x increases. Okay, and this line is that line. We know it cuts like this. So there will be a shape like this. So this is going to be the shape of the graph. X, y, and this line goes, as we know, from here to here. Okay, so this is y squared equals 2x plus 6, and this is y equals x minus 1, and we are interested in this region. So we have to find these 2 points, apparently, and this point. Okay, so first of all, let us find these 2 points. What are those 2 points? Wolfram alpha allowed. Okay, so let's start with this point. What is the x coordinate for this one and this point? And maybe this point. Okay, so let's also find this point. Well, here I'll help you. This part is going to be 0. Where? Here?
Yes.
This is minus 3, okay. So these ones?
This point is unimportant.
Huh?
Second point is unimportant.
Well, first we have to put those things, then you decide whether you are going to use it or.
1 minus 2.
This one, minus 1, minus 2.
Yes.
Minus 1, minus 2. And this one? 5 and 4. Okay, so now let us set up the integral in 2 different ways. One with respect to x and the other with respect to y. In this picture, you see that setting up the integral with respect to dy will be easier. Okay, if you write everything in terms of x, things will be easier. But okay, let's write it. Let's write everything with respect to x first. Okay, area. Now first I'll write this. If we are integrating with respect to x, then I'm interested in this thickness here. So let's use our purple line. So this is my thickness. What is the length of this? What is the length of that line? Given x, so this point is x. What is this point? X.
fx
2 times what?
fx.
Huh? 2 times what? F. What is f? Okay, so the function is this. What is the length y? Square root something, right? So this is square root 2x plus 6. Well, that gives me only this part. I need this part. So area is 2 times that. Okay, so let me write it like this. So the area from x equals minus 3 to x equals minus 1. So let me emphasize that this is x equals minus 3 to x equals minus 1. 2 times square root 2x plus 6 dx. Okay, so that gives me the area up to this part. Now the color of things should change. Let's pass to green. On this part, I am interested in this length. Okay, so if this is x, I am interested in this thing. So this part will go from x equals minus 1 to x equals here, 5, right? X equals 5. So what is the length of this? This function minus this function, right? This function is again, this point is x square root 2x plus 6. Okay, and this point here is x, this one, x minus 1. Okay, so here I have square root 2x plus 6 minus x minus 1 dx. Okay, so this is the area. Okay. Okay, let's now write it with respect to y. It will be easier if we write it with respect to y. Okay, so I'm integrating. Wherever I am integrating, this is the, so let's do it here. For any value of y, this is the length I am interested in. Okay, so remember that we are looking in this way. This is the arrow. So this length minus this point. So this point here is what? If y is this, what is this point in terms of y? If I know the y plus 1, did you look it up in Wolfram? Okay, this point now. Okay, if this point is y, what is the x coordinate? We are solving x from here.
Y square minus 2x.
Y square minus 6 over 2. Huh? I'm taking this to the other side. Okay, and dividing by 2, so that gives me x. Okay, now also area is equal to. Now, from this point to this point, okay, from minus y equals minus 2 to y equals 4. And this number minus well, this side, this number minus this number. Okay, so I have y plus 1 minus y squared minus 6 over 2, 6 dy. So I have, what is this length? I have this length. This length comes as minus. Remember that the arrow is in this direction. So minus this coordinate gives me this length. Okay, so we write these things And the answer is 18. Okay, so you solve this thing, you get 18. You solve this, you get 18. Okay, so in the last 5 minutes I have another. Okay, let's do one last example for areas. Okay, so this is an exercise from the end of the chapter, these plus exercises. So what is the number? Am I following these numbers? 3. Okay, let me write 27 here so the people who are watching this will wonder where the other problems went. Find the exact value of the area enclosed by the curves f of x equals x to the 5 minus 6x cubed plus 4x and g of x equals x. Okay, so first we have to plot this. Before you start plotting, you realize that f of f is an odd function. So whatever it does with positive x, it does the same thing when x is negative, except that it's upside down. Okay, so if we understand the area when x is positive, we multiply it by 2, and we'll get the value. So when you plot this using Wolfram alpha this time, maybe I should not immediately put this. So let me see how I can do this. Okay, so this goes like this, comes down, and then goes up. So it will be like this. And the line y equals x. Okay, let me also draw it with black. So the line y equals x is something like this. Okay, now I can put arrows. This is y equals x. So this is y equals all this thing, x5 minus 6x cubed plus 4x. So we are interested in this area. So you see that if we calculate this on the positive side and multiply it by 2, we'll get the same area because these areas are the same. So we have to find the intersection points. Okay, so this intersection point is easy. I'll write it for you, 0. So what is this intersection point? And we have to find this intersection point. Okay. Suppose I say this is A, this is B. Okay. We'll find exact. So that's why the problem insists that you find exact values. It means that you can solve it. Okay. You see, in order to solve those points, I have to look at, for intersection points, solve f of x equals g of x. Okay, so that's what you do. So this thing equal to this is, and take x to the other side, you have x5 minus 6x cubed plus 3x equals 0. Okay, x equals 0 is a solution, so you have x4 minus 6x squared plus 3 equals 0. So you solve here that x squared is equal to, okay, so 3 plus or minus 9 minus 3. Okay, so you have 3 plus or minus square root 6. Okay, so then x is equal to plus or minus this whole thing, square root of this whole thing. Square root 3 plus or minus 6. Okay, so by looking at the signs of these things, we can tell what A and B is. So let me check what I found for this for this part is. This is square root 3 minus square root 6, and this is 3 plus square root 6. Okay, so the minuses are on this side. Okay, now we can set up the integral easily. Okay, so area, shaded area, is equal to 2 times, okay, we agreed that everything is 2 times. So first from 0 to a, from 0 to 3 minus square root 6, this function minus this function. Okay, so let me just use f of x, f minus g dx, plus, now from this point to this point, 3 minus square root 6 to 3 plus square root 6. This time you see g is, this is g of x, this is f of x. So this time it is g minus f dx. Okay? So you can you can calculate this. You see it's not very complicated because even though the endpoints look complicated, the functions are just polynomials. Okay? You integrate this and you find, so the answer is easy, is 12 square root 6 minus 9. And it's approximately 20. Okay? So even though the solution is not horrible, all you have to do is just attack the problem with what you know until you get a problem. Here, we didn't get any problem. Okay? We just applied everything we know and everything worked out nicely. The only thing that was scary was these numbers, but then who is afraid of Virginia Woolf? Okay, let's take a break.